This is going to be 3/8 beta, and we're going to start with the textbook, pages 166 and 167. Okay, and just to summarize what we have here, what you did in the alpha lesson was you differentiated arc sine, which is inverse sine. We used implicit differentiation. We got this, which you are accountable to memorize. I say memorize. You have to know it in context of a matching scenario. That doesn't really mean anything to you now. But when we get to anti-differentiation, I will remind you of this, and you'll make the connection about what I was talking about with matching. The other part of the alpha lesson is we did the arctangent by the same method, implicit differentiation, and you got a different algorithm for that. So we're moving on today to the arcsecant. Same method. So we have this. Y is the inverse secant of x. It's the same thing as saying x equals secant y. Right? The function is, the trig function is y equals the secant of x. So the inverse function is x equals the secant of y. So we differentiate that. On the right side, we get 1. On the left side, this was on the quiz yesterday, you're differentiating the secant of y with respect to x. So that's going to be the derivative of the secant of y with respect to y times dy dx. And the secant differentiates the secant tan. So then we divide both sides by that. Okay? So by the bottom of page 167, that's combining two sections that were on the quiz yesterday, combining 3.5 derivatives of trig functions and 3.7, which was implicit differentiation. So now what? Well, now we're going to go here. And remind you of this. So here is a table of the trig identities. This is the only one you need to know. The Pythagorean identity is cosine squared plus sine squared equals 1. Because you can rewrite this 3 ways, because there's 3 terms. So here we have 1 by itself. We could rewrite it with sine squared by itself, which I didn't write when it was equal because I don't want to clutter up the column. You can do that yourself. You can solve it for cosine squared. So that takes 1 trig identity, Pythagorean identity, and you rewrite it 2 other ways. Then what? I take this term, 1 over cosine squared, and distribute it over this. So when you do this, you would have sine squared over cosine squared. Well, sine over cosine is tangent, so sine squared over cosine squared would be tangent squared. Cosine squared over itself would be a 1, and 1 over cosine squared is secant squared. Then what? Well, we use this as part of the derivation of the derivative of arctan. So we rewrite it and isolate tan squared theta by itself. It's equal to this. But that's what they're going to use moving forward. So we know what that's equal to. Ready? So we have secant y, tan y. Well, you just saw what tan squared y is. So this secant y, you look up here, is equal to x. Given x. Tan squared was secant squared, take away 1. You don't have tan squared, you have tangent. So you take the square root of both sides. And you get 2 roots. Secant squared y, take away 1. But secant is x. So they put an x. Where the secant was, you get this. You get x times the square root of that sum. However, you really get 2 roots. Because when you take the square root, there's 2 branches, and this is the one expansion where you have to use the absolute value. So in terms of mu, with respect to x, inverse secant of mu is this. But the mu outside the root sign needs absolute value symbols. Why? Because every other time we had a mu for the derivatives of the inverse trig functions, it was being squared. So it wouldn't matter whether it's positive or negative. And this one inside the root sign is being squared. But this is the only term that wasn't squared, so we need the absolute value of this. Okay? And then here's the example. But the example is just procedural. All you're doing is substituting 5x to the 4th where there's a mu. This goes there. 5x to the 4th gets squared. D mu. So what happens? You can drop the absolute value symbol in there because it's x to the 4th to an even power. So you don't need it. If you leave it there, it's not wrong. But it's unnecessary. 5x to the 4th to quantity squared would give you 25x to the 8th. Take away 1 of the root sign. The derivative by the power rule of mu would be 20x to the 3rd. 5 reduces into 24 times. The 3x's in the numerator reduced with 3 of the 4 in the denominator and leave you with this. So the example is just logging in the given value of mu. The challenge is u is following, being able to follow the steps in the differentiation that was done implicitly. But you're not going to have to reproduce that. You're going to have to match those derivatives with the inverse trig function. Okay? And one thing I would caution you about, it's a little deceiving. The heading of the chapter is derivatives of inverse trig functions. You look on the College Board units, there's 2 separate learning objectives. The derivatives of inverse trig functions, but also the derivatives of inverse functions. So you're still accountable for that, and that goes more on what was on the original part of the alpha lesson in terms of the reciprocal. You can look at that, okay? So we're going to pause this. That's your model. You're going to problem number 17. So here's what we got. You just take the algorithm, and where there was a mu, you paste 1 over 2. That's not exactly it. Here it is. You're taking the derivative of t to the negative 1, which would give you negative t to the negative 2nd. So here's the derivative. It's in the denominator. It's negative t squared. That's the derivative. The rest of the problem is algebra. So what happened? In order to do the subtraction, I rewrote 1 as t squared over t squared, so you would have a common denominator. And you would end up with 1 take away t squared over the t squared. Make sense? Then I took this root sign and give each term, the numerator and denominator, their own root sign. Why? Because you can distribute an exponent over division or multiplication. So the square root of this denominator, square root of t squared be a t. And it would reduce with one of these t's out here from the derivative, and then I put the negative in the numerator. Doesn't really matter. So now this term here under the root sign would just be the numerator, and then this t down here would reduce with that t and give you that. And you don't know this yet, but that happens to be the derivative of the inverse cosine of t. What do you notice? The input was the reciprocal. It was 1 over t. So by putting the reciprocal input in there, you got the derivative of the reciprocal function. And that can be generalized to this. But we're back to the array. Sine, cosine, tangent, cotangent, secant, cosecant. And what? If this is the input, it's going to be equal to putting the reciprocal input in the reciprocal inverse trig function. And here, this is just SOHCAHTOA, just to remind you. The sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and so forth. You know that. So what about the ones that were left out? Over here. That's where we are so far. This was the alpha lesson. That's the beta lesson. Okay? And you calculated every other one. And these are homework questions, 32, 33, 34. And you notice the only one that needs absolute value is the inverse secant, because every time you have a mu in the sine or tangent, it's squared. Would be the absolute value. So now the point is, well, is there a more efficient way than doing implicit differentiation to get these three? Good news, there it is. So when I say in context that you have to be able to match these, you only need to match those three. You need to recognize them. And then filling in the other three is going to be very user-friendly if you're going to follow what we do next. So we have this triangle, and the triangle is in the first quadrant of the unit circle. So here comes the circle. Does that make sense? We would go x units to the right, up y, and the radius of the circle is 1. So that would be the hypotenuse of your triangle. But I can't really write this as y, because it's no good to have something with two unknowns. So I'm going to solve that. Using the Pythagorean. I know that, see, I'm saying this is x units to the right. So this squared plus this squared is equal to that squared. Well, 1 squared is 1. This is x squared. What do you add to x squared to give you 1? We have to introduce the 1. You have to eliminate the x squared. So you would add 1 plus a negative x squared to x squared to give you 1. So the height, when you square it, must be 1 plus a negative x squared. So before you square it, it has to be root 1 take away x squared. Then what? Well, from SOHCAHTOA, this angle down here would be the inverse cosine of adjacent over hypotenuse, which would be x over 1. This would be the inverse cosine of x. That's a right angle. This would be the inverse sine of x, because sine is opposite over hypotenuse. So I go down here and I say the inverse cosine of x, this angle, plus the inverse sine of x, that angle, has to sum to pi over 2. Yes? Angle sum of triangle. Because you have a right angle here. So these two have to add up to 90 degrees. Logical? Now, we're not going to do the other two, but they're based on the picture. So inverse cosine, inverse sine are paired up. They have to add up to pi over 2. Inverse tan and cotangent have to add up to pi over 2. Inverse secant, inverse cosecant have to add up to pi over 2 from the same picture. And so can tell. So now we're just going to go here. I want the derivative with respect to x of the inverse cosine of mu. But I know that I can rewrite the inverse cosine of mu is pi over 2, take away the inverse sine of mu from this picture right here. Don't let me lose you. This, algebra 1, at a negative sign, inverse sine of mu to both sides. So to get the derivative of this side, you differentiate this side. Yes? What's the derivative of pi over 2? Oh, you gotta memorize that. What's the derivative of pi over 2? You have to memorize any? Pi over 2 is a constant. What's the derivative of a constant? 0. This differentiates to 0. Yes? Subtract something we already did. So this thing here was missing. The derivative of the inverse cosine is negative 1 times what's above it. Just by doing this. And seeing how these are related, how these are paired up, you could fill in the rest of the table. These two are paired up. So this missing cell, you understand, like I intentionally left this cell blank. I don't want this table to be all filled in and you're just writing it down. It's a bunch of clutter. This cell is negative 1 times that. Let's put a negative 1 in the numerator. This cell is negative 1 times that. This cell is negative 1 times that. And the reason for that is because this relationship right up here how the inverse functions are paired up and they sum to pi over 2. And then you're just doing that work that we did for the derivative of the inverse cosine for the other two. You're going to do the same work. You're going to get pi over 2, subtract the other function. You're going to get 0, subtract what you already did. You get a negative times the one that it's paired up with. Okay. So that's all for 3/8.